Suppose we have a function f of xy defined in a region in the xy plane that's given by a rectangle. So the rectangle I'm going to write like this, AB cross CD. So these two intervals represent the intervals for the x coordinates and the y coordinates. So let's start by sketching this domain. This is a domain of a function, so I'm going to draw the xy coordinates as though the x coordinate is coming out of your screen. And then let's break up the region like this. Say AB, go this way, and CD are over here. And so this region is going to look like a rectangle in the plane that spans between these different values of x and y. So this is our rectangular domain, R, we'll call this. And suppose we have, again, I said a function defined on this domain. For now, for the sake of this lecture, let's assume that f is positive on R. And also that f is continuous on R. So positive means that it's assigning a positive height, and continuous obviously means that there are no jumps or breaks in the graph. I mean, we have a limit definition as well, but just intuitively the graph is nice. So f is continuous, at least on R as well. And so what that means then is that the graph of our function f, so here this arrow is representing what f is doing to the points in the domain, the graph of f then looks like some kind of surface sitting above this rectangle in three-dimensional space. So surface extends over here, it's got some boundary points here and here. So you can imagine that this is drawn properly. I'll try to fix it just so we can get a better point of view here. So up here, this portion, this shade, this that I'm shading right now, this is the surface, and this is the graph of this function f over the region, the rectangular region R. And what we would like to do now is integrate this function over its domain R. We need to think about what the integral should tell us, though. And it tells us exactly what you would think it would. So in Calc 1, in the two-dimensional case, the integral of a function over an interval is the area enclosed between that function and the x-axis. So the same thing is going to be true here. The double integral of this function, f of xy, over the region R, so double integral over the region R, dA, so it's the area, the integrals with respect to small pieces of area in the base. This is going to be equal to the volume of this three-dimensional solid region that we've kind of filled in here by drawing the 1, 2, 3, 4, 5 rectangular sides, and then the sixth side is kind of capped off by the surface itself. So this solid region right here we call E, and the volume of E, the value of this volume of E, that's going to be the value of the triple integral of this function f over the rectangle R. Now to truly think of this as a volume, this assumption that f is positive is kind of necessary. We'll drop that. We'll talk about how to drop that assumption later. But right now we want to talk about how can we compute the volume of this thing. So we'll start by approximating it. And the first step is to chop up our intervals, partition our intervals. This is going to be an integral, and so it's not a surprise that we can partition our interval in the x direction into n subintervals, and each of those x values corresponds to a slice parallel to the y-axis of our domain down here. And we can do the same thing up here. So we can say this is y sub 0, y sub 1, y sub 2, and these choices have to obey the same rule. So this will be y sub capital M, a potentially different number of partitions than we had in the x direction. And both of these partitions have to obey the same rules that they did in Calc 1, which is that x0 has to be the starting point A, has to be less than x1, less than x2, etc., until we get up to the final one. X sub capital N has to be B. And then the same must be true for the y's. So y0 has to be C, and then these have to be increasing. So these are acceptable partitions of our intervals. Again, we are just chopping these up, partitions. And then what we want to do is take a look at one of these sub-rectangles. So maybe this right here is in the ij position. So we'll call this r sub ij. This is in the ij position, the rectangle in the ij position. And we want to zoom in on that and think about, can we approximate the volume of a little box that sits above this sub-interval? Okay, and let's make it an actual rectangular box. Can we approximate this? So can we approximate this volume? So we'll call this Vij. Can we approximate it? All right, I'm going to zoom in on this on the next page, get a little more room, and then we'll write down a formula for this. So again, we have zoomed in on a single rectangular region here, Rij. And sitting above this rectangular region, we have a portion of our surface, which we are going to approximate by a box or a rectangular prism. The idea here, though, is that our surface is kind of cutting through this box right here, and we need to approximate the height somehow. Okay, and so the way that we're going to do this, number one, if this is truly a rectangular prism, then the volume of this prism is equal to the area of the base, area of Rij, times the height of this thing. And so the area we can compute. The area is just going to be a small change in the x and the y direction. So this one will be delta y, let's say delta yj. Okay. And so this will just be, this is bounded between yj plus 1 and yj. And the same thing with this one, our change in x, this is delta xi. That's just the difference between delta xi plus 1 minus xi, that's delta xi. And so the area of the base of this little region is aij. Delta aij is just equal to delta xi times delta yj. Okay, and so the next thing we want to do is we need to somehow determine the height of this prism. So we can choose any point in here. This should feel a lot like what we do in Calc 1. Choose any point in here. This point is going to be a test point. So this will be xij star and yij star. So this is just any point inside the box. So the rule here is that xij has to be between xi and xi plus 1, and that's with a star, yij star has to be between yj and yj plus 1. And it could equal either of the endpoints. That's fine. But we just want to make sure that this point is inside of this sub-box Rij. And then we're going to use this point to determine the height of our rectangular box here, our prism. And the idea here is that this height right here is the actual height from our surface. So this is f at xij star, comma yij star. And this is the actual height at this one point. It's the actual height at this one point. Now that height might not be the same at all these points, but we're going to use that height to measure. So we're going to use that height to be our h over here in our formula. Okay, so that's the height. And so what we end up with is that our little volume element here, which we're going to add up, our delta Vij, this is going to be our height. So f of xij star, yij star, times our change in our area of the base. Remember, the area is measuring the area of the base. The height is measured by the function itself. And so this is delta xi, delta yj. All right, and then if we go back to our picture, that was just the computation of this single volume underneath this one little portion of the curve. We need to add in all the volumes of all these boxes, and what we end up with is, what we end up with is the following formula. So the volume of this region E, this is what we're trying to compute. This is our notation was that this is the double integral over r of our function f of xy dA. This is approximately equal to the sum, as I goes from 1 to n, of the sum, j goes from 1 to m. We need a double sum here because we need to add up the x direction and the y direction of our delta v ij's. And of course this is equal to I, sum I goes from 1 to n, sum j goes from 1 to m of this product, f of x ij star, y ij star, delta xi, delta yj. Okay, this is approximately what we're looking for, and you can probably guess that to get the exact answer, what we have to do is take a limit as the number of boxes approaches infinity. And so here's our definition of our double integral as a Riemann sum. So our double integral over a rectangle of a function f of xy dA, this is equal to the limit as both n and m approach infinity. This could be written as two separate limits if you wish, but as a single limit here, limit of two variables though. I equals 1 to n, j equals 1 to m of this thing right here. Okay, so this is the Riemann sum definition. So this is delta xi, delta yj. Riemann sum definition of our integral, and if you just compare, this is our area element, base times height, delta x times delta y, of the base element. There's our function, and then just like in Calc 1, all of this limit of the sigmas becomes the double S, elongated double S over here. Okay, and so this is, like I said, definition, Riemann sum definition of a double integral of our, in this case we made the assumption that f is positive, but that can be dropped in general.